Hello and welcome to lecture series on electrodynamics. Today we are going to discuss fundamental theorem for the gradients. And it's nothing more than the fundamental theorem for calculus is a three-dimensional extension of the fundamental theorem of calculus. Suppose we have a scalar function t of x, y, z. Is a function of three variables x, y, z, three-dimensional function. And we want to move on a line. Whereas we have a line, say we have this line, and we are moving from point A to point B. And this is distribution, say a temperature distribution, and we are moving from point A to point B through that temperature distribution T, X, Y, Z. And we want to find the change in the temperature or the change in the function T of X, Y, and Z along the way. So we want the change in the temperature or in T, X, Y, Z from through whole section A to B. So if we divide this line into a smaller line, say a smaller patch, so we have this patch and we are going to call it DL1. So the change in T from in this region from here to here, so it will be T dt is equal to delta T dot DL1. So this time we don't have one-dimensional variable for three-dimensional function. To take the derivative, we have to apply the gradient. So change in t is gradient of t time the distance, and so on. We can divide this whole patch, the whole line from A to B to small distances, and we have to reach B. So similarly, if I can put a script t1 here if I want to. So d2 will become delta t dot dl2, where dl2 is this region, and so on. If you have divided the whole line into, say, n, so the change to the nth point is del t dl2. So if I want to change to find the total change or net change from A to B, so I have to add all the changes. Say dt is dt1 plus dt2 plus so on dtn. And using the above definition for dt, it will become dl1 plus delta t dl2 so on to delta t dot dln. And if we convert the discrete domain into a continuous domain from A to B, Then we can convert this sum into integral. So line integral from a to b delta t dot dl. So this is the total change in the function t, and with the definition of the fundamental theorem of calculus. So another way to find the total change in temperature T or function T is you just use the endpoints T of P minus T of A. So this is in fact it is the fundamental theorem for gradients. So again, geometrically, if you want to discuss that you want to find the total change into any three-dimensional function, you can do by either calculating the change at every small step. You can divide the whole path into small regions and find the change at every point and then add them all, or you can just take first and final values or take their difference. So geometrical interpretation is you have the in book the example is given that you want to determine the height of the Eiffel Tower, or you can do it by two ways. The one way is you go by stairs, and then you have to take rise at every stair, every step, and then add up the total rise and the length at every rise. So you have come up with the total height. The second way, it's take an altimeter and just measure the ground point and top point. And take the difference. So either way, you will have the same height for the Eiffel Tower. So that what is the essence of the fundamental theorem of gradient. You can go take the whole path and take the find the change at every point and then add all the changes, or take first and last value of the function and then take the difference. Then you will have the same values. So if we see on the right side, so we have integral del t dot dl. And as the integral is on 2 points, or it seems it will depend on the path. If we will change the path, the integral should change. But if we see the right side, it do not depend on the path of the integration. So it's only depend on the initial and final value of the function. So this special function, or the gradient of the line integral of the gradient of any function, is independent of path taken. So it's only depend upon initial and final value, and this is a special property of gradient. So we can add two corollaries. So the corollaries are, one is L dot T dot DL from A to B is independent of path taken from A to B. Just depends on the final endpoints. The second is, as it's independent of the path, then the closed loop integral del dot del T dot DL must be 0, because in that case you will have to come back at B. So TEA is equal to TB, or TB is equal to TA, and it turned out to be minus 0. So this is the right side. So closed loop integral of the gradient is 0. So we have example 1.9. We have example 1.9, and we are given a function and we are asked to check the fundamental theorem for gradient. So we have a function t, and it's x y square. Then we are given 2 points, point A 0 0 0, and point B is 2 1 0. So we can draw this line path. So we have x y 0 0 point is at origin, and B point is 2 1 2 on this scale, 1 on this scale. So we have the point somewhere here. So we have B. So this is the line, for integration from A to B. And so we want to check the fundamental theorem, and the fundamental theorem is integral delta t dot dl A to B is equal to all right, let's take the left hand side first. So if we want to resolve the left hand side, we need to find delta t first. So for delta t, we have to find partial over partial x t, where t is xy square plus y partial over partial y xy square plus z partial over partial z xy square. So the gradient turned out to be y square x plus y 2xy plus z is independent of z0, or become y square x plus 2xy. So we need to find the line integral. So to find the line integral, we have to consider the integration path. So we can take integration path first. Either we can go straight this way, or either we can take this path. So in book first is solve this one, so we are solving this one. So we have to resolve the integral into two parts. First is the one down one, where we have y is equal to 0 and x is varying from 0 is less than x is less than 1. So if we want to find dl, in general dl should be dxx plus dy y. There is no variation in z direction, so the dz will be 0. So for in this case, as y is equal to 0, so dy will become 0. So the integral dl will become dxx. So we have to find delta t dot dl, and it turned out to be there is no y component. If we will talk dot product here delta t, so only it will turn out to be y square and dx, and y is 0 in this case, so it will become integral delta t dot dl is equal to 0. As y is 0, y square dx will become 0. The whole integral will become 0. So the second path is we have to take this line, and this line is going from in fact this line is going from 0 to 1. In fact here I made a mistake, so it should be 0 to Okay, here we have x is equal to 2. Y is varying from 0 is less than y is less than x 1, and then dl will become x is constant, so derivative of x will become 0, so we will only left with dy y. So if we will take again the dot product of delta t with dl, so it will become, we have to multiply with the y part of delta t, and it is 2xy, and it will become dy. In this case x is 2, so it will become 4y dy, and integration is, so if we take integral delta t dot dl, then integral is from 0 to 1, 4y, and for 4y squared by 2, 0 to 1, so it will become 2. So integral a to b delta t dl is equal to 1 plus 2. 1 was 0 plus 2 is equal to. Now if we check the right hand side where we have to calculate t of b, t of b is t of 2, 1, 0. Let's put these values in function t. Function t is x y square, so it will become x is 2, y square is 1 square is equal to 2. T of a is equal to t of 0, 0, 0. It will turn out to be 0. So integral delta t dot dl a to b is equal to t of b minus t of. Both have the same value. Here we got 2. All right. So we proved the fundamental theorem for gradients, and just you can prove the path independence. And if you integrate on the path where we have this path, so you can integrate from there to there. So this line is, we have to resolve the equation of line, and this will become y is equal to mx plus c, and even you can solve that one, or so it will become y is equal to 1 by 2x, and then dy will become 1 by 2 dx. And if we want to integrate on this part, so integration will be, so by changing the variable, then it will be easy to integrate with the one variable. So if we can write dl in this case, is dx x plus dy y, and now we want to replace dy with dx, so it will become dxx plus 1 by 2 dx 1, and let's take the delta t dot dl with the dot product, then it will become, the dot product will become y square dx plus 2x y dy, 2xy dy. So we have to replace dx and dy. Y is x square, x is equal to 1 by 2y. Yeah, let me see, y is 1 by 2x, so y square will become y x square by 4 dx plus 2x will remain x, y will become 1 by 2 x to 2 will cancel with 2, xy dy is 1 by 2 again dx, so it will become dx. So integration is from 0 to, on this line for x, integration is from 0 to 2, which in the variable in the form of x. So the integration over x will become delta t dot dl integral 0 to 2 x square by 4 dx plus x. We have to replace y, so it is in fact x square. We already x square by 2 dx integration of over 0 to 2. So if we resolve this one, you will find that it will turn to 2, which is the same as we calculated by considering the other part. So again, the integration is independent path for if we have we are going to integrate over line integral over the gradient of some function. So next lecture we will continue on fundamental theorem for divergence. Be sure to subscribe. Thanks for watching.